Microscopes use two lenses to magnify an object. Sometimes they might use more. We call those compound microscopes. Telescopes, the simplest telescopes, use two lenses in order to magnify a distant object. So here we're going to work on a double lens problem. We're going to have two lenses that we're going to use to hopefully magnify an object. Now what we're seeing here is very similar to the problem that we are going to do in lab with our optics bench. Okay, and of course you have a pre-lab problem about it. It's not really representative of what's going on inside a microscope. It's not really representative of what's going on inside a telescope. It's what we can do on our lab bench. But the idea is that you can take an object and then the light from that object can be refracted through both of these lenses in different ways in order to magnify our object. More so than you could with just one lens. Okay. Now, we are going to work through this problem, and there are a couple of strategies that we're going to use. So here's the strategy. The image that we get through the first lens becomes the object for the second lens in order for us to get the final position of that image we would see as the light is passed through or refracted through both of these lenses. Okay, so let's start with some numbers. Let's get us going. So we have two lenses and they're separated here by 20 centimeters. Our first lens, I'm going to call it that here, f1, has a focal length of 10 centimeters. Our second lens has a focal length of 20 centimeters. If you place an object, we're going to place an object 5 centimeters to the left of our first lens, so let's call this distance F1. So we're going to place our object 5 centimeters away from the first lens. So here's my object. I'm going to call this O1, okay? And distance here is 5 centimeters. Where is the resulting image with respect to our second lens here in centimeters? So where, I guess if we put that in numbers, where is DI2 with respect to lens 2? That's what we're trying to solve for, okay? Now, we've got our object 5 centimeters away from our first lens. Okay, so the first strategy is to work on the thin lens equation for our first lens. Okay, so we've got our object. We're going to figure out where the image is created for the first lens. So we'll use our thin lens equation. 1 over f is equal to 1 over di plus 1 over do. And we want to solve this for di. So 1 over di is equal to 1 over f minus 1 over do. That equals 1 over 10 centimeters minus 1 over 5 centimeters. Okay, and so that gives us 1 over di is equal to minus 0.1 inverse centimeters. So we take the inverse of both sides to get us di. So di is equal to minus 10 centimeters. So that tells us that our image that is created by the object for the first lens, that image for the first lens actually appears on the same side of the lens as the object. That's that minus sign here. So I put here the focal length of my first lens was 10 centimeters. My image for the first lens is also sitting at 10 centimeters. So my image is going to be right here on the same side. So it's virtual. But before I draw it in there, let's figure out what the magnification is for the image for the first lens. The magnification we call it m sub 1, is equal to minus di over do. So that's going to equal minus negative 10 centimeters over do, which was 5 centimeters. Remember, do is the distance that the object is from the lens. Di is the distance that the image is from the lens. So that gives us 10 over 5. So that's 2. The magnification is positive 2 for our first image, for the first lens. So I'm going to draw that right here. So this, twice the height of my object, this is the image for lens 1, which is going to be, I'm going to put this here too, this is 10 centimeters. This image is going to serve as the object for our second lens. So the image from the first lens equals the object for our second lens. So now when we think about the second lens, okay, we've got still 1 over f is equal to 1 over di plus 1 over do. We're looking for di, so I'm going to go ahead and solve this, write this down. 1 over di equals 1 over f minus 1 over do. So the focal length of our second lens was 20 centimeters. So this is 1 over 20 centimeters minus 1 over, what's the distance that our object is away from the lens for our second lens? Okay. So remember we said that the image that we created from the first lens is going to be the object for our second lens. So the distance that our object is away from the second lens is going to be 20 centimeters. That's the spacing between our lenses, plus 10 centimeters, which is the distance that this image was away from our first lens. So this entire distance here of 30 centimeters, that equals, I'm going to call that DO2. The distance that the object is away from the second lens. And remember that the image created from the first lens becomes the object for the second lens when you have multiple lens problems. So the distance that the object is away from our second lens is going to be 30 centimeters. The distance to our object for our second lens, we're still going to call that a positive value because that object that we're using for the second lens is over here on the left. Okay, so we've got 1 over 20 centimeters minus 1 over 30 centimeters, and that gives us 1.67 times 10 to the minus 2 inverse centimeters. That's 1 over di. So we take the inverse of that. Di is equal to 1 over 1.67 times 10 to the minus 2 inverse centimeters, and that gives us a value of 60 centimeters. Okay, way over here is where our image is going to be for this double lens setup, okay? But let's just kind of draw some dotted lines here, blah, blah, blah. Okay, so my image is going to be sitting somewhere over here at 60 centimeters. Now, is my image going to be upright or upside down? Okay, this is, I'm going to call this I2, which is actually the image we would see whenever we perform this experiment in lab. We would find the image right here at this distance that we just calculated after passing our object through the first lens and then onto the second lens. Here is where our image would actually appear. Okay, we have to do these intermediate steps in between in order to get to where our final image is going to be for this set of our 2-lens experiment. Okay, now again, is this going to be upright or upside down, this final image here? In order to figure that out, we have to calculate the magnification. The magnification for lens 2 is equal to minus di over do. So it's going to equal minus di, we just showed was 60 centimeters, divided by DO, the distance to the object, which we said was 30 centimeters. Okay, so then we've got negative 60 over 30. That gives us minus 2. So our image, this image, is again magnified by a factor of 2 from this right here, which was the object for our second lens, which was the image for our first lens, okay? Then that means that this final image over here is going to be twice what this one was over here, and it's going to be upside down. So this one's actually going to be kind of upside down like this and pointing that way. It's going to be enlarged by a factor of 4. Okay, because when we have multiple lens systems, the total magnification is equal to the magnification through the first lens times the magnification through the second lens. So that's going to be 2 times negative 2. So the total magnification of this double lens setup is minus 4. So that means that our final image is going to be upside down, and it's going to be larger than our original object by a factor of 4. And so we're going to experiment with a problem very similar to this in lab.